Welcome to the second podcast on fields, this new area of study that we're studying. This podcast is going to be focusing particularly on some aspects of gravitational fields. And just to get going, I've got a very funny clip for us to watch with Wile E. Coyote from Looney Tunes, and you'll notice that it's as if somehow he knows to fall. So let's just watch that now. See how good my internet is. Indeed, very funny indeed. Good old Looney Tunes. They don't make them like they used to. Well, the point of that clip is it's as though an object like Wile E. Coyote knows to somehow just fall to the ground. And this leads into the idea of gravitational fields. Again, this idea that we spoke about in the previous podcast, that in any field, objects experience a non-contact force, and gravity is a perfect example of a non-contact force, because as in that clip, Wile E. Coyote was not touching the earth or touching anything, but somehow it's like his body knew, and they play on this for the sense of humour. It's like the body realises that it has to obey the laws of physics and fall to the ground despite there being no contact. So that's what we're looking at in this podcast. I've just got the study design dot points that are relevant over here. So the first study design dot point is the same one that we looked at in our first podcast, which is describing gravitation, magnetism and electricity using a field model, but I'm just going to put a cross through these ones because we're not going to be looking at magnetism and electricity, just the gravitation part in this podcast. Then it's the third dot point in the study design that's also relevant, so investigate, and I'm going to cross out comparing, because we're not looking at electric fields in this case. So investigate gravitational fields about a point mass. The charge bit is not relevant for us either. So we're investigating gravitational fields about a point mass. We're going to be looking at the direction of the field, the shape of the field, and then I'm also going to cross out these bits. These are things that we're going to come to in another episode. So we're just wanting to get the fundamentals down at the moment. Then the fifth dot point will also be relevant to us, so identifying fields as static or changing. This is something that we've spoken about before, and as uniform or non-uniform. So we've defined that in the previous podcast. If you need a refresher, look at that, but we'll talk about it in the context of gravity. And then finally, describe the interaction of two fields. Again, the electric charges part and magnetic part is not going to be relevant to us, but the masses are to do with gravity, so describing the interaction of two fields, where we know that masses only attract each other. So that puts some context around what we're going to be looking at for this podcast. So let's get into it. Gravitational fields from a single object. So to keep things simple, we'll just start with a single object, and we know that gravity is a non-contact force, as we've just spoken about, and because it's a non-contact force, it's therefore appropriate to use a field to describe it, a field model. And the next thing that's really important is to understand that any object with mass does actually have a gravitational field. Now, I think a lot of you guys probably know this now, but it is a surprise to some people who think that gravity is just the Earth and maybe the Sun or something like that has a gravitational field. But if you're here, you too exert a gravitational field around you. and so I will just draw that very badly. But isn't that cool? You are a source of gravity, just like the Earth. Now the next awesome thing, which I've sort of drawn, although not very well, is that gravitational fields are always attractive. And so what this means, remember we said that the field lines will always point in the direction of the force. We said that in the previous podcast. So that means that the field lines always point towards the mass. The other thing that means is that as long as you have mass, which means you have a gravitational field, it means you are attractive. So who said physics couldn't pump up people's ego? You are an attractive person no matter what anyone tells you. So the gravitational field around a point mass or a spherical object, so either of these things, which includes a planet, will always be radially towards the centre. So my drawing of the gravitational field around a person here was pretty shocking, but having said that, the fact that it was a little bit strange looking and not sort of perfectly towards the centre of the person is actually kind of correct, because a person is not a perfectly symmetrical object. They're not a perfect sphere or anything like that. However, something like a planet, something like Earth, is very close to a sphere, and so that means that the field will always point radially towards the centre. Radially simply meaning along the direction of, if you were to draw a radius from the centre of the circle to the circumference of the circle. So having established those things, we've got 4 questions that I want to work through, and I encourage you to pause the vodcast at any point, try and answer the questions yourself, and then continue on and see how we go. So here I've got a picture of the Earth with the field lines drawn, and so you'll see that these field lines conform to what we've said up above here, which is that the field lines are attractive, meaning they point towards the centre of the mass in there, and they are pointing towards, they point radially towards the centre of the mass in particular. So they're going along a direction which is from the centre of the circle or the planet to the circumference, so that's a radial direction. So looking at those field lines, we can ask, how do the field lines indicate that gravity is an attractive force? Well, hopefully this is a pretty simple one, and you'll understand how we can do that or discuss that, but remember that an attractive force, which we defined in the previous podcast, is a force which makes the objects come towards the source of that field. Now, how do the field lines show that? Well, if we look at these field lines, they are all, each one of them, no matter where you look, they all point towards the Earth. So that's telling us that it is attractive. That's the way that we can interpret the field lines to understand that. Looking at the second question, what do the field lines tell us about the strength of the gravitational field near the surface of the Earth compared with far from the surface of the Earth? So what we're talking about there, I might just get a different colour here. What we're talking about there is if we compare in a region here compared with a region up here, what do the field lines tell us about the strength in those two places? Well, remember what we said in the first podcast was that a stronger field will have lines which are closer together. A weaker field will have lines which are further apart. Now, if you follow these lines back from the Earth away, you'll see that they actually diverge. They get further apart. So we can try and show that as clearly as we can if we just look at this distance between the two lines there and compare that to higher up, that distance. We can see pretty clearly that the distance, the length of that red line compared with the length of the red line closer to the surface of the Earth the length of the red line further from the surface of the Earth is longer. And here it's shorter. So what that tells us is that the distance between the lines is greater as you move further apart, and that should tell us that the strength is weaker. The field strength diminishes as you get further away, which is something that hopefully is what you'd come to expect, that as you move further away from an object, its field will decrease. What do the field lines tell us about the uniformity of the Earth's gravitational field? Well, remember we spoke about uniformity in the previous podcast, and the idea there was that a uniform field will have parallel lines. They'll be parallel. So if we look at all of the field lines around here, we need to ask the question, well, are they parallel or are they not parallel? If they're parallel, then we have a uniform field. If they're not parallel, then we have a non-uniform field. And actually, this question is a little bit trickier than it might appear at first. Our first answer, looking at this picture, should be clearly that it is non-uniform. And the reason for that is the lines are clearly not parallel. We can imagine that at some point they're actually going to all meet in the middle, which means they can't possibly be parallel. And if they're not parallel, that should tell us it's non-uniform. And that's completely correct. However, I'm just going to bring up, actually I meant to bring this drawing up a little earlier. Sorry about this. Let's just bring this one up. So I thought this drawing actually just illustrated, going back to question 2, I thought this illustrated quite nicely the fact that as we move further away, from the Earth, you can see that these circles get bigger and bigger, and that's because of the fact that the space between each of the field lines gets further and further apart, meaning the strength gets weaker and weaker. So each of these red circles sort of represents a point where the magnitude would be the same everywhere along that line. But if you compare each of the red circles, it's getting weaker and weaker as you move further away from the Earth because the distance gets further between each of the lines. Anyway, I'm sorry, I forgot I had that one there, but I just thought I'd come back to it. So returning to question 3 to do with the uniformity, and we've just established that these lines clearly are not parallel, which should mean that the field is not uniform. But I have another image hiding down here, which is this one. So this image is showing us the gravitational field if we look more locally, so at a small patch of the Earth. So you'll notice that the first picture of the Earth that I've shown is looking at the whole Earth, and we know that it is a spherical shape. And each of the field lines are pointing radially in towards it. But we also know that on our day-to-day experience, we don't generally recognize the fact that it is a spherical shape. Just looking around us, it seems quite flat, and that's because it's such a big circle, or such a big sphere, I should say, that we wouldn't really know that. And for the same reason, if we imagine these gravitational field lines in a local region, they actually would be very close to parallel lines as they come sort of from the sky above us and point down towards the ground, towards the center of the Earth. Which is basically like saying that if you are where you are now and then you walk 100 meters away, so let's just show this. Sorry, I need to draw again. So you're here, and then let's say you move over and stand in another place, and let's just say that you're trying to be Isaac Newton here, and so you have an apple, and you drop it there, and then you try your experiment over in a new region here with another apple, and you drop it. What we're saying is that the field is effectively uniform there. The field strength seems the same, which means that the force due to gravity on it in those two places would seem the same. And and the direction would be the same in the sense that it's towards the ground in both cases. So your day-to-day experience would tell you it is a uniform field. It's basically the same everywhere. And we can explain that by the fact that in a local region, the field lines basically are parallel. But if we look at the Earth as a whole, then we would say it's non-uniform, because when we look at that big scale, then the field lines actually aren't pointing in a parallel direction. Final question in this section, which is, what do the field lines tell us about the static or dynamic nature of the Earth's gravitational field? Remember, that idea was to do with whether the field was changing over time. Well, given the fact that our drawing here, the one that we're starting with of the Earth, is just a picture, well, it doesn't tell us anything about the static or dynamic nature, because we would need to see over time, is it changing? And this is just a snapshot in time. So the short answer is, it's a pretty bad trick question that I've asked, which is simply that it doesn't tell us anything. We would need to see how it looks some seconds, minutes, hours, years later to be able to say whether it's static or dynamic. Okay, let's move down a little bit to the last part for this podcast, which is this. So, interactions between multiple gravitational fields. So the idea is, if we have multiple masses in a region, then we'll have a resultant gravitational force, which will effectively be the combined effect of the two masses that are there. And what that means essentially is vector addition. So remember, we said in the first podcast that a field is a vector because it has both a magnitude and a direction. And so when we're combining effects of different fields from two different objects, so like if we had the sun and the Earth, which both have a gravitational field, then we would combine their effects with a vector addition of the different of the two fields. The only thing to keep in mind, which makes this vector addition slightly different to what we've been used to in the past, is that in the past we use the length of a line to indicate its magnitude when we're drawing it. But here, because all our fields are continuous lines, the way that we indicate a magnitude is through the closeness of the lines, not through the length of the lines. So we just need to bear that in mind when we're drawing these. So again, I've got 3 questions here, and again, I'd like you to pause the podcast, see if you can do them yourself, and then return to it and see how you go. So the first question is to draw the gravitational field for 2 equal spherical masses. Okay, so just create some more space for myself. So let's just say that we have an object here, an object here, and we're going to draw the gravitational field for the 2 equal spherical masses. So what I'm actually first going to do is just draw their individual fields, and then I'll show you how we can combine them. So I'm going to draw one of them in green and one of them in blue. So we know, it's easy enough, we know that the fields just point radially towards the centre. But I'm just going to extend these out a bit more because it will become necessary. Alright, and now we'll draw for the second object in blue its gravitational fields. out a bit longer as well. I really do hope that if you're watching this, you're fast forwarding it. It's not exactly riveting TV, but then again, people do seem to choose to watch some pretty exciting shows like My Kitchen Rules. So maybe this is good TV. I don't know. Alright, so these are the two fields that are supposed to be the same within the limits of my drawing ability. And so they should be the same in the sense that the arrows should be spaced apart in the same way for the two objects, and they're pointing radially inwards for both of them. Now, if I want to combine these two, what I need to imagine doing is thinking about adding these from a vector addition point of view. Now, the key thing that I want to demonstrate here excuse me, is that as we move further into this region over here, I think you can tell that the blue field lines are going to be getting very weak. So they're going to be very far apart because we're so far away from the object that's creating the blue field lines. However, we're still relatively close to the object with the green lines, which means that its field is going to be winning. It's going to be predominant. If we go over to this area, the opposite is true. So over in this area, the blue lines are going to be winning and the green lines are going to be very sparse, very far apart, and therefore contributing very little effect. So when we add through vector addition these two fields, what we should find is that we basically end up with the blue field lines in this region and the green field lines in the left-hand region. But what about in the middle here? So in this region, we might expect that because it's essentially the same distance between them, the strength is going to be the same, and that is essentially true. And not only that, but the field lines are pointing for the green to the left and for the blue to the right, and using the idea of vector addition, those components, the left and right components, ought to be cancelling each other out. Now, we should find that because up in the top region here, the green and blue both have a downwards component, so that those vectors will add and create a downwards component, and down towards the bottom, both green and blue have an upwards component, so they should add and give us an upwards force, or field, I should say. But there should not be a left or right component to those fields for that region. So taking all that into account, I'm going to basically undo these bits. Okay, and draw what our resultant field should look like. So our resultant field is basically going to be the... Wow, that was shocking. Again. This is... I promise you, this is far harder than it looks. People on Khan Academy are amazing. So what I'm drawing here, the red lines, are supposed to be the combined effect, the resultant force. Sorry, the resultant field, I should say. And they are essentially the same as the existing field lines for the regions on the outside between the two objects, for the reasons that I said before. But as we look in between here, what we should find is that we get a sort of cancelling effect here so that when we're exactly halfway between the two objects, it's only going to be down or up. I should actually probably draw these two so that they do almost touch, like that. And if we were to look at any other regions, they would sort of follow along closely, and then as you get closer to the object, they would have to pick a path sort of to the left in this case, and to the right if we're on this side of things, because we're slightly closer to that object, as it would end up winning over towards that direction. Okay, so that's quite a tricky thing to do, but it's something that we do need to be able to do, combining the effects of interacting fields. We can then ask the question, is the field uniform? Hopefully that's a very easy no, because these lines are clearly not parallel. The final question, is there anywhere in the region where the field is 0? Well, we said that in the region which is an equal distance from the two objects, the left and right parts cancel out, meaning that our field line is directly downwards above and directly upwards below. But once we get to this point, right here, or really in a smaller region right there, not only is the left and right balancing, but we actually wouldn't have an up or down component to those vectors either, to those field vectors, which means that yes, right here, right in the center, we would have a space where the gravitational field is 0, which is to say that if you went and got in a spaceship between, let's imagine these are two planets that are the same size and same mass, more to the point, and you got right in between the two of them like that, then the gravitational field would be 0 and you would not be attracted to either of them. But if you then went and found yourself in a spaceship right here, then you would end up following whatever the field line was in that position, so you would end up getting attracted to that planet there. So that's what that is showing. Okay, I again hope that that's been helpful. If you've enjoyed the podcast, then feel free to support it in any way that you can. Sign up, tell everybody how amazing it is, and I will see you next time. Thank you very much.